Welcome to the presentation on the beta distribution. Our group is consisted of Hui, Brandon, Mackensie, Haibo, and I'm Nick. So what is the beta distribution? The beta distribution is actually a family of continuous probability distributions because it has shape parameters. It is defined on the interval 0 to 1, and the parameters a and b control the shape of the distribution. The beta distribution is the conjugate prior probability distribution for the Bernoulli, binomial, negative binomial, and geometric distributions, meaning it can be used to represent initial knowledge about the probability of success in another distribution. Essentially, it can represent a probability distribution of probabilities. The probability density function for the beta distribution is as shown below. The random variable x is said to have a beta distribution with shape parameters a and b, which are greater than 0 if its density is given by f of x, which is equal to x to the power of a minus 1, multiplied 1 minus x to the power of b minus 1, all over the beta function of a and b, while the value of x is between 0 and 1. Otherwise, the value of f of x is equal to 0. The beta function, beta ab, is a normalization constant that ensures the total probability is 1, depending on what the shape parameters are. This constant can also be written in terms of the gamma function. Beta function ab equals the gamma of a plus b over the gamma of a multiplied by the gamma of b. The cumulative distribution function for the beta distribution, or CDF for short, cannot be written in closed form, but by definition it is f of x, which is equal to the integral from 0 to x of t to the a minus 1 multiplied by 1 minus t to the power of b minus 1, all over the beta function ab and multiplied by dt. And that is with respect to the value of x, which is in between 0 and 1, and with shape parameters a and b greater than 0. This is sometimes written as ixab, which is called the incomplete beta function. The quantile function, likewise, does not have a closed form either. The expectation, or the mean of the beta distribution, is a over a plus b. As we will see later with a few examples, if a is greater than b, then the mean will increase and the distribution will be skewed to the right. If b is greater than a, then the mean will decrease and the distribution will be skewed to the left. The variance of the beta distribution is ab all over a plus b squared multiplied by a plus b plus 1. And the standard deviation is just the square root of the variance. The moment generating function for the beta distribution, or mx of t, is equal to the summation from k equals 0 to infinity of t to the power of k multiplied by beta a plus kb divided by k factorial multiplied by the beta function ab. That is equal to 1 plus the summation from k equals 1 to infinity of t to the power of k divided by k factorial, all by the multiplication series from n equals 0 to k minus 1 of a plus n divided by a plus b plus n. Skewness and kurtosis can be used to describe the shape of a distribution. Skewness is the degree of asymmetry of the data. For example, a negative value typically indicates the tail is on the left and the mean is shifted to the right, and a positive value is the opposite. For the beta distribution, the skewness is defined by 2 multiplied by b minus a multiplied by the square root of a plus b plus 1, all over a plus b plus 2 multiplied by the square root of ab. Kurtosis is another way to describe the tailedness of a distribution. Since the kurtosis of any univariate normal distribution is 3, most people use the excess kurtosis instead, which is simply kurtosis minus 3. The excess kurtosis for the beta distribution is defined as a minus b squared multiplied by a plus b plus 1 minus ab multiplied by a plus b plus 2, all multiplied by 6. And that is all over ab multiplied by a plus b plus 2 multiplied by a plus b plus 3. If we are given a random sample from a population and we want to figure out if it fits the beta distribution, we can estimate the shape parameters a and b based on the mean and variance of the given data using the formulas a equals 1 minus mean over variance minus 1 over mean. B, or beta, equals a multiplied by 1 over mean minus 1. Coding the beta distribution in R is fairly easy. In the stat package, there is a beta distribution script that anyone can copy. In it, there are several functions that can be used to plot along with the beta distribution. d beta is the density of the beta distribution. This means that the y value for a particular dx results from the amount of times the probability for that x value is calculated. This also means that the y value can be greater than 1. However, if you scale this down, it does create the PDF of the beta function. Instead of having the function count how many times a particular instance of data appears, it may count relatively how many times data may appear, which will calculate the PDF. P beta is the CDF of the beta distribution. This function easily calculates the CDF as a built-in function in the stat package in R. Q beta is the quantile function of the beta distribution, also known as the inverse CDF or complementary CDF. Q beta and P beta mirror each other along the line x equals y, as in the examples later. R beta gives random data samples that conform to the specified beta distribution. The code is set up for inputs a and b as the inputs for the beta function. The function will make a sequence for x. It will then create data points for the density function, CDF, quantile function, and generate random numbers adhering to the specified beta function. It then plots the data. Below the pl.beta function are calls to the function. This generates the plots that can be seen in the following slides. The first example we will take a look at is when a equals 3 and b equals 1. The blue line represents our randomly generated data. The graph should be a scatter plot, so all the points where the line has kinks are the locations of the data with respect to y. From this randomly generated data, you may notice the blue line never goes above the y value of 1. These points, with respect to y, are the probabilities at the points in the distribution. You may notice that the points with respect to y are typically closer to 1.0, with fewer points close to 0.5 and even fewer close to 0.25. This is related to d beta, the black line, which shows that more points should be located closer to 1.0 with respect to the x-axis. The CDF is shown as the red line and quantile function is shown as the green line. There is a line where x equals y that shows how q beta and p beta mirror each other. In our second example, we have a equals 2 and b equals 4. Our randomly generated data shows most of our data is within the range of 0.1 to 0.5. As you can see from the black line, the density of the randomly generated data should be about the same. This time, it is easier to see how the CDF relates to the density function. So as the density function increases to about 0.25 with respect to the x-axis, the CDF, or the red line, gradually increases to about 0.25 on the x-axis. From this point onward, the density starts to drop off and the CDM remains steady to about 0.6 with respect to the x-axis. As the density significantly drops the closer it gets to 1.0 on the x-axis, the CDF gradually decreases the amount it is incremented until it finally converges to 1 with respect to the y-axis. The last example shows similar shape to the second example. This time, it has more data points on the blue line closer to about 0.3 on the y-axis. The density is steeper at 0.3 where it reaches its highest point, decreases as it gets to 0.5, then flattens out towards 1.0 with respect to the x-axis. The CDF shows that it starts to increase gradually towards 0.3, then increases steadily to about 0.5, then starts to level out around 0.6 with respect to the x-axis and converges to 1 with respect to the y-axis. Like we said before, the beta distribution is a continuous probability distribution that models events which are constrained to take place within an interval defined by a minimum and maximum value. The beta distribution can also be used to represent proportion or probability outcomes. These include a range of disciplines such as rule of succession, Bayesian statistics, and task duration. Examples of events that may be modeled by the beta distribution include the time it takes to complete a task, the proportion of defective items in a shipment, how likely a candidate will receive a certain percentage of the vote, and my favorite, baseball batting average. For those who are unaware, baseball batting average is the number of base hits divided by the number of times a player is up to bat. From his article, Understanding the Beta Distribution, David Robinson, who we will cite later, goes into how the beta distribution can be helpful in determining batting averages in baseball. One must first note that the average batting average is about .266, while .3, or 300 batting average, is considered really good. David uses the values 81 and 219 to represent the values of A and B, respectively. He uses these values because, as he shows in his article, 81 over 81 plus 219, or 300, equals 0.27, or close to about 0.266. As you can see in the plot, the distribution lies almost entirely within 0.2 and 0.35, the reasonable range for a batting average. But that's just the first step into determining why the beta distribution is helpful in batting averages. Imagine a player gets a single hit. His record for the season is now 1 hit for 1 at bat, or a 1 batting average. But that's not entirely sustainable. Using the beta distribution, he uses 81 as A naught and 219 as B naught. To whereas if a hitter goes 1 for 300, or a 333 batting average, he now uses 81 plus 100 as the A value and 219 plus 200 as the B value. Note how the resulting curve is now not only shifted to the right, but also thinner. This is because we have a better estimate as to what the season batting average will be. As you can see on our last slide, our updated estimate results in about a 303 batting average, while our naive estimate is at a 333 average, and our original estimate to start the season is a 2.7 average. This is because, using the A naught and B naught values, we give the batter a quote-unquote head start, as David would say, to the season, knowing that we have a predicted value of what the average should be. Thank you for listening to our presentation of the beta distribution. Once again, our group consists of Hui, Brandon, Mackensie, Haibo, and Nick. Thank you.